This video is about the properties of continuity. Basically, if you take two functions that are continuous at C, then all of the functions pictured here will also be continuous at C. In other words, if you have a function that is continuous at C and you multiply it by a constant, the resulting function will also be continuous at C. If you take two functions that are continuous at C and you add or subtract them, then the sum or difference will also be continuous at C. If you take two functions that are continuous at C and you multiply them together, then the product will also be continuous at C. If you take two functions that are continuous and you divide them, then the quotient will also be continuous at C, as long as the value of the denominator does not become 0. And finally, if you take the composite of one function at the other, then the composite function will also be continuous, as long as g at c does not cause function f to be undefined. For example, consider the function f of x equals x plus sine x. You can picture this as being the sum of two functions, x and sine x. Well, we know that the function x is continuous over all real numbers, and we know that the function sine x is continuous over all real numbers. So automatically then, the sum of these two functions will be continuous for all real numbers. Since x is everywhere continuous and sine x is everywhere continuous, then x plus sine x is everywhere continuous. Example 2, look at the function f of x equals x squared plus 1 over cosine x. Again, we can look at this as two separate functions, this time being divided. So we have one function, x squared plus 1, being divided by another function, cosine of x. X squared plus 1 is a polynomial, and polynomials are everywhere continuous. And cosine of x, which just goes like up and down forever, we know that cosine is everywhere continuous. So if we make a quotient of these two continuous functions, the resulting function will be continuous everywhere as long as the cosine x does not equal 0. So just to repeat, since x squared plus 1 is everywhere continuous and cosine x is everywhere continuous, then the quotient x squared plus 1 over cosine x will be continuous everywhere except where, of course, cosine x is equal to 0. We can't have a 0 denominator. Think about the function f of x equals sine of 3x. Now, we can look at this as the composite of two separate functions. The first function would be sine x, and the second function would be 3x. Now, if we imagine taking the second function and substituting it into the first function, then we get the following composite function, which would be sine of 3x. Now, taken separately, the function sine x is continuous everywhere, and the polynomial function 3x is also continuous everywhere. So the composite function sine of 3x is also going to be continuous everywhere. Again, since sine x is everywhere continuous and 3x is everywhere continuous, then the composite function sine of 3x is everywhere continuous. Look at example 4. F of x equals the square root of x squared plus 1. We can look at this as the composite of the two functions, square root of x and the function x squared plus 1. Since the square root of x is continuous on the interval 0 to infinity, and x squared plus 1 is everywhere continuous, then the composite function square root of x squared plus 1 will be continuous everywhere. Normally, I would have to mention some restrictions to make sure that we don't have any negative numbers under the radical, but because of the x squared, we're always going to have a positive number under the radical. So x can just be whatever it wants to be, no restrictions. In fact, here's a quick glance at the graph of this composite function, and you can see that it is continuous everywhere. Example 5 is very interesting. We have a piecewise function, f of x, which equals the sine of 1 over x when x does not equal 0, and it equals 0 when x does equal 0. Now, focus on the sine of 1 over x part. We know that this function would be undefined at 0 by itself, because 1 over x is undefined at 0. You can't have a 0 denominator. But that's why we have the second part of the piecewise function, which solves that problem. At 0, the value of the function will simply be 0. So with that second part, the function f of x is now defined everywhere. There's no value of x for which f of x is undefined. Now, does that mean that f of x is everywhere continuous? Well, not so fast. The function sine of 1 over x is a very interesting function. And even though with the second part of the piecewise function, we have defined what happens at 0. So the value of the function when x is 0. Boom, we have this dot right here. So even though this piecewise function is now defined at 0, I submit to you that it is not continuous at 0. The reason why is, remember that in order for a function to be continuous at 0, the limit as x approaches 0 from the left has to equal the limit as x approaches 0 from the right, and then both of those limits have to equal the value of the function at 0. The problem is, the limit as you approach 0 from the left does not exist, because the function keeps alternating back and forth between positive 1 and negative 1, positive 1, negative 1. It never stops switching back and forth. The closer you get to 0, it keeps alternating between positive 1 and negative 1. Same thing as you approach 0 from the right. There is no limit because the function does not approach a single value. It just keeps switching. So, because there is no limit as x approaches 0 from the left or from the right, the function is discontinuous at 0. However, the function is continuous everywhere else. So, because the limit as x approaches 0 of f of x does not exist, f of x is not continuous at 0. However, f of x is continuous on the interval negative infinity to 0, union 0 to infinity. In other words, it is continuous everywhere except for 0. Example 6 is identical to example 5, except for now we have this extra x factor in front of the sine of 1 over x. Now, in the previous example, we had a discontinuity at 0. The question is, will this x factor somehow affect that and make the function continuous? So let's focus on this part of the function where we have x times the sine of 1 over x. Now, remember that when we talk about the sine of 1 over x, it looks like this picture right here, where it's cycling back and forth between positive 1 and negative 1 over and over again forever as we get closer to 0. So we can think of this as having x times some value between 1 and -1. So the question is, what happens as x approaches 0? What happens as x gets closer and closer to 0? So really focus on these x values for a minute. Here are a couple of samples. Imagine an x value of 4, and then 2, and then 1, and then 1/2, and then 1/4, etc. All right? The point is, x is getting closer and closer to 0. Now, the part of the function where we have the sine of 1 over x, we're just taking these x values and we're multiplying by some value between 1 and -1. Remember, what happens when you multiply by 1? Nothing. What happens when you multiply by -1? It just switches the sign. So something in between those two effects will be happening at most. This 4 is not going to become a 6. At most, it might change to a -4. So multiplying by the sine of 1 over x will affect the sign, but it will not affect the absolute value. So these could be positive or negative depending on where we are in the cycle. But the general trend as x approaches 0 is that this is going to be getting smaller and smaller. All right, the sine of 1 over x part is just affecting whether it's positive or negative. But it's going to be smaller and smaller. It's going to be approaching 0. So it sounds like we have a limit on our hands. So here's a graph to help you see what I'm talking about. Notice the closer we get to 0, even though the function is switching back and forth between negative and positive, the absolute value is getting smaller and smaller and smaller. So if we talk about limits, we could say the limit as x approaches 0 from the left of f of x is equal to 0. All right? You see it shrinking. It's getting smaller and smaller. It's getting closer to 0. And the limit as x approaches 0 from the right is also 0 for the same reason. And then, of course, because of the second piece of the piecewise function, which tells us that at 0, well, at an x value of 0, the value of the function is 0, that fills in this one dot right in the middle, which keeps the function from being undefined like it normally would be at 0. And we get that the value of the function at 0 is 0. If the limit of the function from the left is equal to the limit from the right, and that's equal to the value of the function, then that is the definition of continuous. So we see that f of x is everywhere continuous, from negative infinity to positive infinity. The last property of continuity that I wanted to talk to you about is called the intermediate value theorem. Now, this is one of those things that the first time you read it, it doesn't make a lot of sense, but then once you examine it more closely, it becomes like common sense. So, the intermediate value theorem, if f of x is continuous on the closed interval from a to b, and if f of a does not equal f of b, and if k is any number between f of a and f of b, then there is at least one number c in the interval from a to b such that f at c equals k. Wow, okay, what in the world did I just say? First of all, the setup. They're saying f of x is a continuous function on the closed interval from a to b. So here I've drawn an example of a continuous function on the closed interval from a to b. They're saying that f of a does not equal f of b. So notice that this first point right here, this is the value of the function at a. This is f of a. And down here, here's f of b. So I've drawn it so that there's some space in between these. That's all this is saying. F of a and f of b, there's got to be a gap between these two values. Now, here's the heart of it. Given this setup, they're saying if you pick any number k that is between f of a and f of b, if you pick any number k that's in here somewhere, then that is going to correspond to at least one value c that is between a and b, such that f at c will give you k. So what am I saying? If I pick any k value, all right, I'm just going to draw this line out so you can see what I'm talking about, then that's going to correspond to at least one c value. So for example, right here, notice where my k line hits the function right here. If I drop it straight down, that's going to correspond to a c value, such that if I did, if the value of the function at c is going to equal k. All right, if I go to this c value, look, there's the function at k. So in other words, if I pick any y value that's between these two y values, there's going to be at least one x value that corresponds to it. Notice that the intermediate value theorem does not tell me what the c value is. It just tells me that at least one exists. Also, it doesn't tell me how many c values there are that will correspond to the k that I pick. In this case, if I pick the k value right here, there happen to be 3 c values that correspond to it. But the intermediate value theorem does not tell me that. So one more time, the bottom line is any k value in here is going to correspond to at least one c value in here. So for our last example, let's look at a typical problem where we might use the intermediate value theorem. Does the function f of x equals x to the third power plus 2x minus 1 have a 0 on the interval, the closed interval from 0 to 1? So first of all, this is a polynomial function, so we know it is continuous everywhere. So it will definitely be continuous on the closed interval from 0 to 1. Let's help ourselves keep track of what's going on with a little sketch. All right, so obviously here is 0. I'm going to go ahead and put 1 out here. And we are doing the closed interval. So let's look and see what the value of the function is at 0 and what's the value at 1. So if we do, let's see, if we do f at 0, what are we going to get? So f at 0 means we're substituting in 0 for all of these x's. So that would just wipe out this term, and that's just going to leave negative 1. Let me just clean that back up. All right, so we're seeing that f at 0 is going to equal negative 1. So I'm going to go ahead and put that down here. All right, so here's negative 1, and this is f at 0. All right, now let's take a look at f at 1. All right, if we do f at 1, we're substituting 1 in for all of these x's. So that would be 1 to the third power plus 2 times 1 minus 1. So let's go into that a little bit more. So this would be 1 plus 2 minus 1. We see the 1 and the negative 1 cancel each other out, so that's just going to equal 2. All right, so I'm just going to mark that up here, by the way. So we're seeing that the value of the function at 1 is equal to 2. So at 0, the function is at negative 1. So basically, I have this first endpoint right here. And then at 1, the value of the function is at 2. So that's going to be like up here somewhere. We don't know exactly what the function is doing between these two values, but we know that the function is continuous. So I'm just going to connect those dots to illustrate that the function is continuous between these points. So when we talk about zeros of a function, we're basically talking about x-intercepts. So the intermediate value theorem tells us that if we pick any k value between f at 0 and f at 1, and we're going to go ahead and pick the k value of 0, which is the x-axis. So if we pick any k value between here and here, there's going to be at least one c value between here and here that corresponds to it. In other words, there's going to be at least one 0 between here and here according to the intermediate value theorem. So we can conclude that yes, f of x does have at least one 0 on the closed interval from 0 to 1, because according to the intermediate value theorem, if f at 0 is negative and f at 1 is positive, there will be at least one c value between 0 and 1 where the value of the function is 0.